Okay, so in this example, it says that in 2011, the U.S. Census report determined that 71% of college students are working students. A researcher thinks this percentage has changed and surveys 110 college students. The researcher reports 91 of the 110 are working students. Is there evidence to support the researcher's claim at the 1% significance level? So there's a couple of things going on. So the first thing we want to do is make sure the preliminaries are met. Okay, so the first one is taking the sample size n. So they sampled 110 college students. Is this no more than 5% of all college students? Right, in the US, actually, specifically. I think so. Yeah, definitely. Check. Okay, so we can assume that the samples taken are independent. The other one is the sample size of 110 because, and I just want to make sure that we are on the same page here. So because no mean or standard deviation is given, I automatically assume that we have a proportion. So no mean, no standard deviation, you can assume it's a proportion. And so no, sure enough, they do give us a proportion, the 71% as the P, right? And then they survey 110. So the survey of 110 students and a population proportion of 0.71 of the U.S. college students' work is NP times 1 minus P greater than or equal to 10? So that's what we need to check. So we have 110 times 0.71 times 1 minus 0.71. So go ahead and put that in the calculator. So you would just put 110 times 0.71 times and then 1 minus 0.71, and that equals 22.649. 22.649, which is greater than or equal to 10. Yes, we can assume samples are independent and that the population is approximately normal. Great. Okay, so now all preliminaries are met, and so therefore we'll go ahead and start the hypothesis test. What are we doing? Well, no mean or standard deviation. We are doing a proportion. Okay, so the first thing we need to do is always the hypothesis, setting up the hypothesis. So the null, H sub 0 is, and what parameter? Don't put mu, right? It's a proportion, so put P. And we claim, what is status quo? U.S. Census says, I don't care what you think, 71% of college students work. So P is 0.71. The null, or the alternative, is what we want to claim, right? What's the change? So a researcher thinks that a percentage the researcher thinks that the percentage has changed. Well, what does that mean, right? So let's go all the way up here and see. So the parameter equal to and then not equal to, that would mean different. Less than means less than, and then greater than means more than. So different would just mean that we don't know if it's increased or decreased. We just know something's different. So we would have a two-tailed test with not equals in between. So this would be, let me put it in red, not equal to, and it's the claim, so mark it. So part 2 would be to draw the figure, and then we can identify the 1%. So we'll put 0.01. So if the population proportion is given to us as 0.71, and it is a two-tailed test, right? So it's two-tailed. And so what does that mean? Well, it means I have two tails. That's all it means. It means that there's something over here. And something over here in the other tail. So if 1% is in both tails, then what is in each tail? Well, 0.01 to 0.005. So there's 0.005 in here and then 0.005 in here. And so we're doing a proportion, so it's z sub alpha over 2. So here what we're saying, there are two critical regions. And so if the p-value lies to the left of the tail or in the right tail, then we say this is statistically significant. Okay, so now drawing it, it's not equal to, therefore it's a two-tailed. We split the alpha into the two tails, and these two are the critical regions. So step 4 is going to start the approach. So the first thing we would do, we'll do the classical approach, and then the p-value approach, and then the confidence interval approach. So I think the first thing we should do is go to the calculator and run that test, and then get all the stuff that we need out of it. So let's gather all the information that we would need. We know that the population proportion is 0.71. We know the number of people sampled is 110, where 91 met the attribute that they were working students. And then we know our significant, and then we know it's a two-tailed, right? Not equal to. Okay, let's go to the calculator. Because it's a proportion, we'll go to stat and test, and we have to go down to the one prop z test, which is number 5. So what they want is that population parameter, 0.71. They want the number of people who are working, right, the number of students, 91 out of 110. We had a two-tailed test, so highlight the not equals, hit enter, and then calculate. So let me go ahead and drag this scene over. Oh, God. Okay, and let's go ahead and hit calculate, and then we get all our data. So let me go ahead and drag this over. And let me go ahead and make it smaller. Okay, so the classical approach says that a couple of things, right? So here is our test statistic. So t is equal to 2.71. Okay, and we need to compare that with, So we have z equal to 2.71, and we need to compare that to z sub alpha over 2. Because it's symmetric, we can just do z sub alpha over 2 is just going to be the inv norm, right, to find that statistic with a tail of 0.005, comma 0, comma 1. We can just use it, it doesn't matter, and then because it's symmetric, we just do the positive and negative of that number. So let's go ahead and do that. Let's go ahead and second bars. Let's go to inv norm. Let's put that area in. and then 0, 1, and then just, you can keep it right, and then just paste, and then enter. So that z-score for a tail of 0.005 is 2.56. And so this number here is 2.56, and this is negative to the normal curve is symmetric. So here, does this lie, here's 2.56, and then here's negative z sub alpha over 2, which is negative 2.56. So if I wanted to take and compare, is this in the critical region? Where does z lie? Well, let's go ahead and take a look at our picture. Here's 2.56. Where is 2.71? Is it in here, or is it in between? Is it in between negative 2.56 and 2.56, or is it greater or less than these? Well, 2.71 is definitely greater than 2.56. So the test statistic z lives in the critical region, and therefore we expect to reject the null. So because the test statistic is greater than the z sub alpha over 2, the critical value with the critical region, we have to reject the null. And it becomes statistically significant. So we just are testing z-scores and the critical value, but it's the same approach to p-value. So let's do the p-value next. So this was classical approach. Let me box it. I'm going to have to scroll down a little. So now let's go ahead and do p-value approach. Right? And here the p-value from the calculator is 0.0067, and alpha was 0.01. So once again, if I compare alpha to the p-value, I can see that 0.006 is less than the alpha, and that this means that if I took a random sample, most likely that it's going to be less than making a type 1 error, and so there's going to be some sort of change. And so here I would reject the null. And that would be it for the p-value. Now let's go to the confidence interval approach. So the confidence interval approach just states that go ahead and find the confidence interval, and if 0.71 lies in that confidence interval, you're good to go. If it doesn't, that means it's outside of it, and therefore it doesn't even lie in the confidence interval. We have to reject the null then, because that's just, it's not going to work, you know? So we want to make sure that p equal to 0.71 is in this confidence interval, right? In between the lower bound and upper bound, right? Then you're okay, right? Do not reject the null. But if here's like the lower bound and upper bound, and if p is somewhere out here, then you have to reject the null. Okay, so we'll go ahead and find the confidence interval in the calculator. Let's go to our calculator, and we go to stat, and we go to test, and we'll go to one prop, right, z int. So we have to just keep going down, and it's a, right, one prop z int, hit enter, and we just put x, n, and grabbed it already from our hypothesis test, and our confidence level is 1 minus the alpha. So if alpha is 0.01, that means the confidence level is equal to 1 minus 0.01, which is 0.99. So we'll put that in the calculator. It seems like it's, so let's just hit calculate. And let's drag that over. And so notice that if I drew a number line, here's the lower bound and upper bound. This lower bound is 0.73 and this upper bound is 0.92. And we say, well, this would be like 90, we are 99% confidence the population proportion lies in this interval. So P would lie in here somewhere, right? But what was our P in our case? The P was 0.71. Where is that? That 0.71 is right here. Is that outside our confidence interval? Yes, right? So therefore, if it's outside of our confidence interval, this is statistically significant and we reject the null. So no matter which approach you use, so that you have p-value, a classical, and confidence interval, you will obtain the same results. It's just really the student's preference. Again, the homework and every chapter forward, we will be using the p-value, so I encourage you to use the p-value. If you get help from other means and they use different approaches, at least you have an idea of what they're saying, but just kind of give a heads up saying, well, we're going to be using p-value here. Okay? So now the last thing to do is now just make a conclusion. We're only going to do one of these and then make a conclusion. So now we can go ahead and go to step 5. So now step 5 would be to interpret. So no matter what I'm doing here, I'm rejecting the null hypothesis. Let's go back up here and see what that looks like. If I reject the null, that means I'm only left with the alternative. The alternative was the claim. Therefore, is there enough evidence to support the claim? Yeah. So we could say that there is enough evidence to support the researcher's claim that the proportion of student workers, I should say students who work, right? Or working students, right? Has changed from a 0.71 or changed from 71%. I mean, we don't know what it is, like if it's greater than or less than, but we just know it's different than the 70 from the US Census 71% data.